So we're going to start with here, and I want to focus on bringing stuff from Inventor just to start off here, and we'll talk about different aspects of what simulation mechanical can bring to the table here. So to start off, just looking at a simple part here in Inventor that as I'm designing this, this is a symmetrical part here. I just cut it in half so it makes it easy. And I'll keep the model simple here so we can actually see live demos here instead of having to record stuff. But with using simulation mechanical, if you've used Inventor FEA, we know it's environments, stress analysis. With using Inventor, we have the ability to use a static analysis, and we also have modal analysis, which are great tools to get design to check different things that's on the static side of it. But what I want to look at is actually bringing stuff across into simulation mechanical. Now, to do that, basically, different tab up here, there's Autodesk Simulation. I can launch this active model. And kind of showing this, I'm just kind of focused on bringing it from Inventor. And I'll kind of show you what else we can bring in here in a second. But as it comes across here, we saw with Inventor, we have the static stress and we have modal in there. The top three basically you can do with Inventor Pro. You can kind of see the different options down through critical buckling loads, some random vibration, stuff like that. You can do linear analysis on. Nonlinear, we can get into the MES, which is the event simulation with nonlinear materials, or static with nonlinear materials. We'll talk a little bit about thermal side of it, steady state and transient, and then we got electrostatic analysis that we can run in here. To start off, I'm just going to bring this part in just as static stress, just as the starting point here. And when it comes across from Inventor, it's just bringing the model straight from Inventor over to simulation mechanical. And we can notice I can flip back to Inventor and see that, come back in here. If I don't have Inventor on my machine, not a big problem. We can just open straight in simulation mechanical. You can come bring in Inventor files, CATIA, IGES-STEP, DXF, ProE, SolidWorks, and so forth, so that it can bring across a lot of CAD files that we may need to use simulation tools for. So I don't have to have Inventor here. But since I'm using Inventor, it makes it easier. So a lot of this in simulation mechanical, just kind of a quick run through this, is a lot of this starting left to right. When I bring a model across, I'm going to mesh it. So I'm going to break it down into the meshing. And this part will run really quick here. And I'll keep it at a larger mesh so it runs quick in here. But setup side of this, all I need to do is come in here, look down through here and say, okay, well, here's my part. It's created, and it's actually brought that mild steel across from Inventor. So if you remember, yeah, mild steel Inventor, it came right across and it's happy with it. I can change it in here. So if I want to edit that and say, I want to use their library and say, bring in A36 just for the fun of it. And just overriding that, but that's fine. So a lot of this is to set up the model, set up, or click on the Setup tab up here. So to start off, I'm just going to set it symmetrical. I can select this, and if you like to right-click, I can always come in here and say, well, yeah, it's symmetrical about X symmetry. Or I could select this face and come up here and say there's a pin constraint here. So I can set this information up, and I know there's a bearing load on this face. Again, right-click or pick the buttons up top. It's just preference. So that way, if I said, let's call it 2,500 pounds in the negative Y direction here. So visually, we can see what's going on with this. So that we've got a test set up is just knowing, hey, pin constraint, it's symmetrical about that face, and we've got a force going down. So all I'm going to do is say, run this thing. So as it runs it, doesn't take it too long with this simple part here, but we're going to get results back in here. I want to take a look at them. It's pretty quick here. So that first inspection, displacement, 0.006 inches. So I mean, that's kind of what I expect. I forgot to show you that this is a 1-inch thick plate here. So it's a pretty beefy plate here. So a lot of this with analysis, anybody that does these, you can kind of see, let's make sure it animates fine. It looks like I would expect in there. So we can set that and see, let's look at von Mises here. It's only 3,600 pounds of pressure there, so it's about a safety factor of 10. So I mean, it's pretty good. I mean, it's way past what we need on this. So so a lot of this information is the fact that if I kind of tested this, I realized, well, I got plenty of strength on this to see what loads it's going to see. Well, maybe I needed to change something in Inventor. Maybe I need to cut the weight down on this part. So if I looked at back in editing here, if I go back to Inventor, let's maybe come over here and say, let's cut some holes in it, see if we can relieve some weight in here. So that if I have holes in here, I want to push that back across. So what I'm going to do is just say, yeah, launch active model again. So as this launches it again, jump back over here and you'll see it's thinking on it. And it comes across and it's doing its meshing, it's remeshing it for me. So that it kept my constraints, my loads, got the new holes cut into it. So all I have to do is say run the analysis. So that way we can get new results with those 3 holes cut into it. So that way we can see if we can alleviate some of the weight that way. And we can see it's still 4,100, so I mean we're still pushing a safety factor of 7 with this one. So that maybe, since this is a 1-inch plate, maybe I want to narrow that down. Easy way, I could go back to Inventor and do it that way too, or since it came from Inventor and it's an Autodesk product, we have Inventor parameters came across with it. So my parameters from my model, since it came from Inventor, if it came from Step, SolidWorks, anything like that, wouldn't have this. But if I came in here and said, let's take that thickness down to a 1/2 inch, let's update my model. It's going to think and narrows up my part here. So it's changed the geometry inside of here, but if I look back in Inventor, nothing's changed here. It's only on the simulation side. So that way, I'll redo the mesh here. So it keeps constraints, everything. Let's run it one more time here, just a quick test here. So now we see around safety factor of over 3.5 there, so that way 8,200. A lot of this visualizing this stuff on the results here, we could easily go in here and say, well, let's mirror this thing so that we can see what it actually really looks like since we're doing symmetrical. Of course, you can animate and see what's going on with this thing. So that way we can test our design in here to figure out what's going on with it, just jumping back and forth from Inventor just to try some stuff. So that way if I know I need to take some weight off of it, test it, see what it does. Simple parts like this, it's pretty quick, just a simple analysis to see that where things are heading in there. But for this one, actually, go ahead and close that out. I want to check another thing that we can do in Simulation Mechanical. On Inventor, I'm going to open up just a 2-part assembly here. So the same steps, I want to bring this across. So that way, static stress. And as it comes across, I'm just going to mesh this real quick. What I want to do is just, if I wanted to bolt 2 plates together in here, over on Inventor's FEA, I'd have to have the bolt modeled to actually hold it together in there. Here, what I want to do is just, let's say I'm going to constrain these 2 ends. So those 2 ends are going to be fixed. So it's locked down on both sides of it. If we look at our browser in here, anything red is just usually a flag saying, hey, you need to change this. Because if I look at my analysis, I can't run anything as long as something's red out here. So it looks like, hey, I didn't set up my materials in Inventor. Well, I might as well do it here. So if I run, let's go put 836 on there again. So it's happy it would run right now, but I haven't added anything. And all I want to do is say there's a force. Let's go negative Y direction. Just pull on the face. Not too accurate with this one, but I just want to have some kind of force pulling down on this one. And we can see when it came across, it said these are bonded. No, I just want them surface contact. So I want them to be able to have a surface contact between the 2 of them. I could also go to settings and include friction with that. Right now, I just won't include it. It'll take a little bit longer to solve in there. But to handle these bolts, Inside Simulation Mechanical, we have a bolt generator that we can come in and say, well, here's the surface that the head of the bolt is. Here's a surface for the interior hole and the surface for the nut. So that way we can control what's the bolt diameter, what's the head diameter, what's the nut diameter. And then the nice part down the bottom, you have a preload magnitude. So if there's an axial force or a torque you want to put onto it, there's a 100-pound force on those. All right. So it creates it, and it creates beam elements to represent the bolt. So that if I wanted to throw it on one other side here, generate that, and I can redo the mesh so that way you can see it'll line up with the nodes on these guys. So that we can see our analysis grayed out. It's one definition for those bolts. So I need to know what material it's going to use. Let's go in here and select just to be consistent here. And then tell it to run real quick. So as this runs, a lot of this didn't need to do any modeling for the bolts in there. I just configured it here so that way I can put preload forces on it. It doesn't take it too long to run here. So you can kind of see those. And I'm going to turn the bolts off so you don't have to see it. So we can kind of look in here. And you can see it's separating from each other in there. So that way we know, yeah, it's pulling apart. If I expand out the over-exaggeration of this, that might have been a little too far, but you can kind of see where it's pushing in and pulling away on that side. Let me actually bring that back up some. So we can see what's going on there, but the bolted connection there is a great tool with the FEA that I wish the Inventor Pro had it in there, but it doesn't yet. But the other part of this is just the freedom on the analysis side to come in here. Let's just do a slice on the XY and translate that so we can just kind of see down through that hole. So if we scroll over here and kind of look into there, we can see what's going on inside the part. We can change it and actually see our meshing in there. So you can see how the meshing created through there. You can see the holes kind of slide across each other a little bit as it goes across in there. But the nice part is the fact that we can slice these to see inside the part to see what's going on. We can actually select elements. So that way, turn that off. If I wanted to remove a certain group of elements, I could hide those so I could see what else is going on inside different elements in there. So that way, we can turn elements on and off to see what's going on with our part, to kind of see inside to make sure that it's acting the way we expect it to. So a lot of that you can kind of manipulate a little bit more with the simulation mechanical in there. So for this one, we'll jump out of that one and run through a couple more things out here. One, kind of flip through some of the options in there. That if I want to look at, say, a steady state heat transfer. So if I'm dealing with applying heat to my parts and seeing how the temperature is actually going to go across my part, or maybe how it's going to affect the integrity of the part, we can do that. And you can see this one. Let's scroll this up here. You can see the steady state heat transfer. All of our parts are set up with materials. And this one's already finished, so we don't have to wait on it. But a lot of this, we have a convection across the surface of all the fins out there. And then we have a certain temperature that's on the end of, apologize for that, but the end of our part, we actually have a fluid in there. We have a model of the actual liquid in there with the properties set up. So that way, when we run this, we can see how it's actually cooling down as it runs across here. So if it starts at the constant temperature flow, we can start at 120, it's going to get down to 92 on this side of it. You can always come through these probes to find out the temperature across the way. So we know how it's affecting this fluid. If I turn the pipe on, we can see how it affects the pipe as it's going through there and so forth. So that way we can see how temperature is affecting our parts or how maybe we need to cool it down more and so forth. So that way, steady state is great to see how the heat's transferred at a basically a steady state in there. If we wanted to start dealing with time, maybe we want to look at the transient heat. So that way, if I open this up, anytime you're dealing with time, it gets into the MES side of this. So that way, in here, if you look here, you can see it's transient heat transfer in there. There's convection load on the exterior, and there's convection on the interior. And that's the only loads that are on this. So that way, I'm at results out of date, but we can still see them. We can see over a time step of 6 hours, and to show you here, in the setup of our analysis, we have our thermal loads, but we have parameters that allow us to actually set up, yeah, I'm going to run this for a 6-hour time frame and have 12 steps. So I want to see every 30 minutes of how it's reacting in there. So now if I jump back to the results, you can see how it's reacting over time. And this time when I hit animate, it's actually animating the time frame in there. So you can kind of see the temperature adjusting in there over a certain time frame. So a lot of this is, yeah, we've dealt with the time, but how is that affecting our model? If our model expands, contracts, is that going to affect any stress on the part? So a lot of that, all I have to do is go back to the FEA editor. Let me see if we can create a brand new simulation over here. So the mechanical event. And when this one comes across, it's just the MES with nonlinear material models. So that we can set this up with the pen constraint, and it's holding it on the other side so it doesn't move in the X direction in there. But there's no heat analysis over here. But the nice part of this is parameters. We can always come across and say, well, yeah, we want to bring in some thermal analysis from another design scenario, another simulation mechanical file. You can even bring it from simulation CFD to transfer the information across to this. So with that information, we could run this and see just by the heat on there expanding, what kind of stress are we seeing on a part in there. So on this one, we can kind of see Max is sitting in here on the inside corner there. But the nice part here is we can actually map this stuff across time in here. So that way we can see what's going on with it. I can pick any node out here. I can graph that value. So that way it kind of shows you where it's kind of spikes in the temperature. Then over time it just kind of cools off in on that area. Over here you can kind of see it kind of flatten around 32, 3300 and somewhere in there. So that way we can see that, yeah, over time it got hotter and expanded, but then it kind of calmed down there. It wasn't affecting the model. So it's about 32,000 pounds stress that's seen in there. And you can animate these too. So that only thing on this is just the heat. That's the only thing affecting the stress on this. So that way we can do steady state heat transfer just to kind of see if we know, hey, my part's going to see some heat. Let's see how it's going to react in there. And of course, always add the time factor in there too. That we can test those as well. The other side of this, kind of the last one I want to show you here, is if your parts move, they can react differently on different things. So let's save that one. I'm going to open this one up. So on this last one here, it's just kind of looking at basically a forklift of how much stress are we seeing on the forks as we're lifting up objects in there. Yeah, I could do a static analysis and just say, let's push 500 pounds down these and see how it acts. But is that the true reaction of this part as it lifts something? So with the MES, the nonlinear material models, we're doing an event simulation with this one. So again, it's just basically working on time. So if we look at parameters, you can see this. For a 5-second analysis, we want 100 different time steps in there. So all this one is doing is a displacement. It's lifting this thing up for 5 seconds. It actually starts like a second into it and so forth. So that way we can see how it reacts with this. So if I look at the results here, look down the side of it here. If I hit the animate button, you can kind of see that it starts for a good second. You can kind of see it kind of bounces a little bit there, but starts lifting up. Once it stops, you can see the weight of the box kind of springs back and forth in there. So it's seeing some stress from that thing just bouncing up and down in there. So what kind of stress we can see, let's actually stop that and look at von Mises here. I know the max is in that corner, but I'll show you anyways here. So if you want to look at that point, I right-click on it, graph that value of that node. You can kind of see it ramps up. There's different aspects in there, but looking at that, I don't know at what points what, so I can actually close that. The easy part is I'm just going to embed this graph, so that way I can see it down here, and I can actually hit the animate button at the same time, so I can see at what point. So right when it started to lift it, it kind of spiked, and I guess that right where it stops, where it kind of bounces, you can kind of see the stress on there. So that way, of course, I can actually resize this thing too, so you guys can see it better. So as that thing's moving, you can kind of see what's going on with it. And over here, we can refine that so that we have a lot more sample sizes here, so we can kind of see a little bit more of how it's actually running in there. So, so a lot of that with the MES side of this is being able to run simulation with something that's moving in there. Yeah, it takes longer to solve in there, but it allows you to see what's going on with your parts. Some of these in here, I go back to FEA editor, there is drop test wizard, so you can actually, if your part drops, it'll help you set that up so that way you can see what's going to react to it as it falls in there. So a lot of those kind of help with the MES side of it when you're dealing with motion. Static stress, can handle it here, can handle Inventor Pro, have a little bit more flexibility on this side of it with the mesh, actually a lot more with the mesh side of it. But so there's a lot you can do with it. It's just knowing you can bring stuff straight from Inventor, you can bring it from any other CAD package out there. But just to run a quick test on something, just to prove a point, so that if you're always building something that's just beefier than it needs to be, test it, prove what you're seeing, so that way, hey, maybe you can drop some weight on it because it's cheaper, lighter. We might want to look into that. So a lot of this kind of wound up 5 minutes shy here, but a lot of this, as we go on any of this stuff, any questions you have on this, feel free to email me or anybody at D3. They can get a hold of me, or anybody else can answer these. But if you have questions on anything, feel free. I know I've kind of flown through this stuff. I just kind of throwing some information at you there, but you can kind of see my email up there. Feel free to shoot me an email if you have a question on anything. A lot of this webinar, we don't usually have the questions, comments here, but if you have questions, feel free to email me in here. But other than that, hopefully this is beneficial to everybody. If you got some information out of it, that was helpful. But so I appreciate everybody's time, and hopefully I'll be talking to some of you at some point. So thank you all for attending.